So, let us get started with today's lecture. This would be on KL transforms. So, you have seen at least two transformations as part of this course. One is the Fourier transforms and the other is the wavelet transforms. We have gone into the detail. Of course, you have Z transforms, Laplace transforms and many other transforms that you have studied as part of your electrical sciences courses. So, in today's lecture we will see what is common between these transforms and then we will delve into the KL transform, Karhunen-Loewe transform. So, if you see the broad structure, right, many transforms that we are familiar with have been signal independent. This is a very important thing. Many transforms we are familiar with have been signal independent. That is, we have a broad or generic framework to handle any signal with some properties associated with them. Example, convergence, etc. such that the transformation yields A, energy compaction, B, perhaps better analysis, or I would say signal properties in the transformed domain. So, a good example of energy compaction is wavelets, right. You think about wavelets, they compact energy, and because of some compaction of energy which is happening, that is, you look at the original band and then you split it into two bands, right, high pass and low pass, and again perhaps within low pass you further decompose into low pass and high pass and so on. You do this level of decomposition as much as you want so that you can have energy in the topmost subband, right, and that basically, I mean, you have all the energy concentrated in the region, in the subband region that you want up to the level of resolution that you intend to, right, and that is basically energy compaction, and that leads to automatically to compression. And another example that we saw was analyzing the signal properties in the transform domain, right. So, for example, if you look at wavelets, if I give you a 63 hertz versus perhaps a 65 hertz, you would give a certain emphasis to 63 hertz versus 65 hertz, though it is just 2 hertz of separation, they are binned and compartmentalized in different subbands, right. There is some sort of unequal resolution that we can place, right, and this gives us better analysis. It can also give spike suppression, etc., etc. So, therefore, signal properties can be better analyzed in the transform domain by using the frequency domain tools like the Fourier transform, etc., right, and we have seen such properties. Now, one of the questions that we have to ask is there a framework where the transformation depends upon the data, right. So, this is a sort of a philosophical question to ask. So, one is a regular transformation. I give you any signal, I can compute using Fourier transform, that is a signal independent, right, as long as it satisfies certain notions of convergence, right. Example, you know, it is absolutely integrable or square integrable, we have different notions that we place for the signal, right, as long as it behaves is well behaved within those notions of convergence, then we can compute the transformation and then we can analyze further, right. Now, what is the main issue with data independent transforms versus data dependent transforms, right. If you think about data independent transform, irrespective of the signal, as long as they are satisfying certain properties, we can do energy compaction, we can compress, we can transform it into the equivalent domain, figure out what it is required, etc. But one of the questions that may come is, if we were to maximally compress in some way in a signal processing framework, compression can also be thought about from an information theoretic framework, right. There are entropy based compression engines, that is out of the scope of the current course. But if you think about from signal processing perspective, statistics of the signal should play a role for certain, if you were to look at certain properties of the signal in terms of compression, etc. And that is the reason why people conceived data dependent transforms such as the principal component analysis, which is also the KL transform. Okay. So, philosophically put, is there a transform that can A, yield energy compaction, that means you compact the energy into a set of few coefficients that you want. Okay. Next is decorrelate data. Correlations are good if you want to sense intelligence, right. If you are bringing an intelligent machine, if there are correlations or patterns that are correlated, you can predict. A good example is, if you have gone through the course and you try to correlate with the professor's scheme of examinations, you can predict what can come. If you cannot correlate, then probably you can't expect what the type of questions can be, right. So, this is, I think, is an important, we need to decorrelate data. We would like to have unitary transformations because it eases out certain properties in terms of simplifications if we can. So, therefore, we bring this notion of unitariness, which means if you are given a linear transformation A transpose is identity. And then this is very important, it is data dependent. That means statistics of the data must play a role. Okay, if you pose these problems, I need a transformation and I would make it more specific as a linear transformation, because we like to play with linear operators. Okay. We need a linear transformation that can do all the following. That is, it should be able to do energy compaction, decorrelate data, maintain unitariness, and then it should be data dependent. So, if you satisfied all these things, then we have a transformation, right. And fortunately for us, Karhunen and Michel Loeb, this is 1948, this is 1947, they developed this notion of, this is for K, and this is L, Karhunen Loeb transforms, okay, named after the inventors. So, we will study the properties of KL transforms, we will study the properties that leads to KL transforms, set up the problem in the framework of optimization that automatically leads us to the transform. So, I think it will be a two-step approach in the lecture. So, first we will study some properties and then we know the answer to some extent, and then we will pose the right problem and then we will derive the transformation from first principles, okay, and it has a lot of applications. PCA is a very well known algorithm in machine learning, and the applications from search engines to many things you can do with PCA, okay. So, let us start with the following. Let us imagine vectors x belonging to Rn, right, they are column vectors, n dimensional vectors, and they are associated with some probability density function, okay. So, to be precise, they are column vectors. Now, we can compute the covariance of x as follows. So, sigma x is the covariance matrix of x, which is expectation of x minus mu x times x minus mu x transpose. Okay, so this is a matrix, right? This is an n by 1, this is a 1 by n, you have a n by n. So, this is a covariance matrix. Now, suppose we consider a linear transformation of x by a. Let a be some linear transformation of x, which means y equals a times x, right, familiar transformation. So, this implies if you take the expectation of y of this is expectation of a times x, which is basically this is mu y, we will designate it as mu y, which is a times mu x, right. You can pull a outside because it is not stochastic, expectation over the random vector, right. When you take expectation, you should look at the multivariate distributions right, because it is a vector, it has several coordinates, and you should look at the multivariate density. Now, sigma y is expectation of y. If say covariance, you have to remove the mean, right, we have to remove the bias and then we have to compute the expectation y minus mu y times y minus mu y transposed. This is what we need to compute. Now, we plug this in, y equals ax, and we will simplify. Sigma y is expectation ax minus a times mu x times ax minus a times mu x transposed. Now, we can pull a outside here, expectation x minus mu x times, this is a into x minus mu x transpose, the whole thing transpose, this is a b whole transpose is b transpose times a transpose, right, and we can write this as x minus mu x transpose times a transpose, okay, because just a b transpose is b transpose a transpose, we apply this property. Now, I think this brace must be here, okay. This is a times sigma x times a transpose. This is how we would compute the covariance of y. So, we are slowly building what we need, what our goal is, right. So, we will start with the following goals. So, say what we may need. 1, we may want y to be decorrelated that is sigma y is a diagonal matrix, say lambda, right. We want to decorrelate the data. That means if you look at one coordinate, it is not having any correlations with the other coordinate. I mean, you take the expectation in the stochastic sense. Now, second property is we still need energy compaction that is place energy of the signal non-uniformly that is from high to low over the signal dimensions. So, what do we mean? Suppose data is such that let us say it is a 2-dimensional data, energy in x is 95% versus energy in y, right. If you take the sum energy, that has to be 100%, right. If you look at all the coordinates, if you look at the energy in each of the coordinates, that should be the overall energy in the system. but some of the coordinates may have more energy than the rest, and we need some way in which we can sort of have a gradation in the energy over the coordinates, right. That is sort of the, I would say, an idea. Now you get these 2 points, right. We have these 2 goals now, and we want a linear transformation, right. You can question that if you proceed with a nonlinear assumption, your optimization will be according to what you started off with, but often having a linear constraint helps us. Okay. So, let us proceed further with this. Let psi be a unitary transformation matrix. For goal 1, we can achieve diagonalization if y minus mu y is linearly related to x minus mu x. Right. We can achieve diagonalization if y minus mu y is linearly related to x minus mu x. So, suppose y minus mu y is some psi inverse x minus mu x. Let us choose psi to comprise of eigenvectors of sigma x. So, in a way I have given you the answer for this linear transformation. It is basically stacking all the eigenvectors of the covariance matrix of x, right, but we will arrive that this is indeed the right transformation to choose with the set of optimization constraints that we have. Okay. So, now if we assume this solution, right, then sigma x times psi is psi times lambda. I call this equation A. Why? Because of course we can say sigma x times some, say psi I is one such vector, right, is basically lambda I times psi I. This is your eigenvalue equation for I equals 1, 2, 3, so on n till n, right. You have n coordinates, you have n eigenvectors and eigenvalues, and this is the eigenvalue equation, and you stack all these lambda 1, lambda 2, lambda 3, it becomes a diagonal matrix of lambda, right. Lambda is basically diag, this lambda is diag lambda 1, lambda 2 dot lambda n. Okay, and then you can compute. Similarly, you stack the corresponding eigenvectors and you can get this. Now, sigma y is psi inverse sigma x times psi. This is not too difficult to solve, right. I mean, all you have to write it in terms of expectation of y minus mu y times y minus mu y transposed, these are vectors, right. So, and you use this solution that y minus mu y is psi inverse of x minus mu x, right. You plug this here, you will end up with expectation of psi inverse x minus mu x, x minus mu x transposed, and then you have a psi here, right. Expectation is over this, so it is basically psi inverse expectation of x minus mu x, x minus mu x transposed times psi, right. This is just aside some steps. Right, just follow the math, you will land up with this. Okay. Now, we are able to achieve our goal of forcing sigma y to be lambda by an appropriate transformation A equals psi inverse. Right, we can get a diagonal matrix. I mean, we can say that if sigma y is going to be lambda, we can say the sigma y is going to be lambda if A is chosen to be psi inverse. Okay. Now, let us, so we got a hint already, that is you take the data x, that is random vectors x, pool them up, compute their covariance matrix, get the eigen decomposition for the covariance matrix, stack all the eigenvectors, and that forms your linear transformation, okay, for mapping x to y. And let us investigate the properties of y, and we should be able to have decorrelation, etc., etc. Okay. So, let us prove some basic properties associated, and then we will carefully delve into the rest. Property 1, for any real matrix A, so it is a real, and I also need to bring in the symmetric property, real and symmetric matrix A, eigenvectors are orthogonal if eigenvalues are distinct. An interesting property, right. I give you a real symmetric matrix and I compute, I do the eigen decomposition, right, and eigenvectors are orthogonal if eigenvalues are distinct. And why do we have to bring in this real symmetric matrix? What is the connection? Think about the covariance matrix, right. Expectation of x1 x2 is the same as x2 x1. So, if you start transposing it, you will see symmetry properties there, unless you are bringing any data dependent notions on the coordinates itself in some way that may not give you the kind of structure that you want, right. Normal conditions, expectation of x1 x2 is same as expectation of x2 x1. Okay. So, let us prove this property, and that is the link where we are building. This is more a general notion to state this property, but keep in mind that this matrix A, you have to imagine the covariance matrix, because that is our goal, that is how we are proceeding. Okay. So, let us start with the proof. Consider the inner product of Ax with y for vectors x and y that are eigenvectors. Now, since A is symmetric, A equals A transposed. Okay. Now, inner product of Ax with y can be written as Ax transpose y, right, it's a dot product, and this is going to be x transpose A transpose y. Let me call this equation 1. Now, equation 1 can be seen slightly differently, right. So, I can see this as x, need to put in these vectors here, x dotted with A transpose y, right. So, by our definition you transpose this and multiply with this, right, that is what we did here. We took Ax, we transposed it and we multiplied it y and we got this, right. I can interpret it like this, x with A transpose y, but this is symmetric matrix, A transpose equals A, I can write it as x with A y, right. So, Ax with y is same as x with A y if A is a symmetric matrix. Okay. So, let us call this equation 2. Let Ax equals lambda x and Ay is some mu y. Okay. Now, Ax with y is basically lambda, because Ax is lambda x, right. I use the property that I can pull the scalar out, lambda inner product of x with y. Similarly, I have x with Ay, this is mu times, I pull the Ay is basically lambda mu y. So, I pull the mu scalar outside, this is again x with y, right. I have set of equations 3. Now, they both are equal, right. That means, if I take the, if I subtract these two equations in set 3, that has to be 0, but lambda is not equal to mu because we assume that they are distinct. This implies inner product of x with y has to be 0, which means from geometric sense x is orthogonal to y. Such an interesting result, which says that the eigenvectors are orthogonal. And you know what is the deeper implication of this result? Because they can form a basis. Right, and that is why people think about it as eigenbasis from that perspective. Okay. Now, let us check if the energy conservation holds. This is very, very important, because if you cannot satisfy the energy conservation property, then there is some loss in the transformation, right, and we cannot recover. Now, the energy in X is basically the covariance which is given by expectation of x minus mu x transpose times x minus mu x. Now, let us consider energy in y, right. Energy in y is Ey, which is expectation of y minus mu y transpose times y minus mu y, right, with y equals psi inverse x, where psi inverse is some matrix such that psi inverse equals psi transpose. Let us say this property is satisfied. Now, Ey is expectation of x minus mu x transpose psi inverse transpose psi inverse times x minus mu x, and observe this, because we wanted to bring in the unitariness, right. A transpose is 1. So, your A is like psi inverse and A transpose is like your psi inverse transpose, or your A is psi inverse and then A transpose is psi inverse transpose. Because of this is unitary, this is identity, and we have seen this unitariness in filter banks as well, right. So, therefore, Ey is expectation of x minus mu x transpose times x minus mu x, and this is basically Ex, and the implication of the statement is energy is conserved. So, this is a very important property that you have to bear in mind. When you do these transformations, you do not want to lose the original energy in the signal in the transformation. The energy has to be preserved, but you decide what components you want to throw them off, right. You decide which of the how much of energy you want to retain, and depending upon your threshold you decide what you can do with the representation. So, this picture should be very clear in your mind. Now, with some of these properties that we saw, we will motivate towards the derivation of the transformation. Suppose we want to compact, this is very very important, compact energy within the first q components of y can be construct a transformation that does this. That means I take some transformation of x and I get this vector y, and I will observe the energy in y, I want to compact it within the first q components of y. Some transformation is happening such that say 95, so let us say the dimension is 10, the first 5 components has 95% energy and the rest has 5. Say suppose I want to realize such a kind of transformation, can I do that with the given properties? And you have already seen how statistics is playing a role here, because we are bringing in the covariance matrices of the data. So, therefore, we are bringing data dependent statistics, right. We have to apply other properties and motivate this problem. Now, to be more precise, suppose A is a linear transform such that y equals Ax. Let us assume A is such that I have a stack of all these vectors where a u is a n by 1 column vector. Okay. Say suppose. Now, let us deal with Hermitians because they can be complex valued. So, therefore, we can think about Hermitians. Now, a Hermitian, so instead of real symmetric matrix, I could, instead of real I can bring in perhaps complex, and when I bring in complex, then you have to be careful when you do the transposition, you have to take conjugate transpose, right. That is the only subtle detail. So, just to be mindful about. So, now A Hermitian is this matrix which is A naught conjugate A1 conjugate dot 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 A n minus 1 conjugate. Okay. Now, to consider energy in the first q components of y, let us null out k greater than or equal to q components, I would say greater than q, because you want to retain the first q and then anything post q you want to null out components in A and A Hermitian. Okay. Now, let us form a q by retaining the first q components, and this is A naught A1 dot 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 A q minus 1 0 0 0 transposed, and a q Hermitian is this matrix which is A naught conjugate A1 conjugated dot 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 A q minus 1 conjugated null null null. Now, what we need is we need to maximize the energy within the first q components, which means we want to look at the expectation of x minus mu x Hermitian with AQ Hermitian AQ times x minus mu x subject to the following conditions, which is AK conjugate transpose AK is 1, it is ortho normal conditions, that is the inner product between two eigenvectors that are not the same is 0, and when it is the same it is normalized to 1, right. Otherwise I would have had, if I considered, if I didn't null everything, then I would have just a full A, right, in this. If I would have had a full A here, right. Since I am nulling out components k greater than q, right, then I retain the first q components, and therefore this is the energy in the first q components, and I want to figure out some transformation that can maximize the energy in the first q components. It is maximize Ey of q, which is given by this quantity subject to these conditions, subject to these conditions. Okay. So, now it is not too difficult, we can take and formulate these into the Lagrange multiplier framework. Let us see how we can do this. Now, J is maximize AK conjugate k equals 0 to q minus 1 of Ey of q subject to the condition this is 0. That is, you bring in the condition that AK conjugate transpose AK equals 1, and that is the equation. There is the associated parameter lambda k for the Lagrangian. So, you have all such equations, q equations for k equals 0, 1, 2, 3, so on till q minus 1, and you set that within the constraint setup. So, now to simplify, let us compute some terms, and one of them is AQ Hermitian times AQ. So, this is basically A naught conjugate A1 conjugate dot dot AQ minus 1 conjugate nulls times A naught transposed A1 transposed dot 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 A q minus 1 transposed, and then everything is null. Okay, and this can be compactly written in the form of a summation. This is k equals 0 to q minus 1 AK conjugate times AK transposed. Okay. The moment you understand how to set this right, the rest is routine algebra. I mean, you just have to get the right setup formulated. Now, J equals maximization over all AK conjugates, K equals 0 to Q minus 1, expectation of x minus mu x Hermitian summation. So, AQ Hermitian times AQ can be written with the summation k equals 0 to Q minus 1 AK conjugate AK transpose times x minus mu x, right, and then subject this to the following constraints. Correct. All I did is, this looks more messy than what we started off with, but of course sometimes doing a lot of messy things will give you good results. You can simplify things carefully. It looks a very ugly equation, but you can simplify this. Now I will call this equation 1. Let us rearrange 1 a bit. Let us rearrange this a little bit. Okay. So, to rearrange this, we need to consider x minus mu x, because the ugly term is one which is in this expectation, right. I consider x minus mu x Hermitian times AQ Hermitian AQ times x minus mu x, and I said this could be written as summation k equals 0 to Q minus 1 x minus mu x times, there is a Hermitian here, AK conjugate times AK transposed times x minus mu x. Now this is very important to just recognize the fact that this is a scalar and this is a scalar, and you are taking two scalars and you are multiplying them and you are basically adding them. So therefore, if I can reverse the scalars, so what I can do is the following. I can rewrite this as summation k equals 0 to Q minus 1 AK transpose x minus mu x times x minus mu x Hermitian times AK conjugate. So that is why routine algebra will not help you. Somewhere you should pause a little bit and think, what if you can simplify this further, and this simplification will help us because we can write J, I would call this as, I said this is earlier was equation 1, okay, let us call this equation 2. Using 2 in 1, we can write J as maximize over all AK conjugates k equals 0 to Q minus 1 expectation, I have to bring this expectation now, summation k equals 0 to Q minus 1, I just drop in this directly, drop in 2 here, AK transposed x minus mu x times x minus mu x Hermitian AK conjugate. Okay, I want to maximize this subject to these constraints. it looks still messy, but we can simplify because you can pull this expectation inside. Expectation is a linear operator, right? That property we will apply. Now J, let us simplify 3. So by doing so, what we land up is now J can be written in the form maximize over all AK conjugates k equals 0 to q minus 1 summation k equals 0 to q minus 1 AK transpose. Expectation is pulling inside. So, the expectation of x minus mu x Hermitian x minus that is becomes sigma x covariance matrix times AK conjugate subject to these constraints. This is now easy for us, right, where sigma x is expectation of x minus mu x times x minus mu x Hermitian. Right, this is straightforward. Now what we do is, I would call this 4. Now to solve for equation 4, so you want to maximize something subject to this, you set the partial derivative of this cost j with respect to AK conjugate to 0 for all k equals 0 1 dot 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 q minus 1, right. You do this and you apply the properties of the vector differentiation, that if you have two vectors y and x, d by dx y transpose x is basically y. Now using this property, dj by dak conjugate equals 0 implies sigma x with ak minus lambda ak equals 0. And this is our eigen this is our eigenvalue equation. So all we did is we post the solution to the linear transformation in the framework of optimization subject to certain constraints. This is basically a constraint optimization problem, and then we land up with the eigenvalue equation. So before we started off with the optimization, we never assumed that they are eigen, they are 0 or they are eigenvectors, etc. They satisfy this equation. We assumed that we wanted them to be orthogonal. We wanted so that it forms an easy way to represent in the form of a basis. So if we brought in the orthonormality constraints and subjected the energy to be maximized over the first q components, and we did this, we land up with the eigenvalue equation. So it is okay to choose eigenvectors of the covariance of x and then work out backwards to get to our transformation. So I really do not know how Karhunen and Loew thought about in their original thought process of thinking through this problem. Did they have an intuition that they have to look into the eigenbasis, or they just posed it in an algebraic framework and solved this. I do not know how they went ahead, but I think remarkably there should have been some clear intuition behind going about in a very structured way to solve this problem, right. So, this concludes the KL transformation. We will now see the application of KL transformation to dimensionality reduction. Okay. So, we will stop here.